1.5 Sums of series. Now, you can use results about the sums of geometric series with complex numbers. Now, let's suppose you've got a geometric sequence. We have over here our first term, which is a. The term after this, assuming we have common ratio r, will be ar. The term after this, we have ar to the power of 2. We're multiplying by r each time. Term after this, we have ar cubed, and we can continue this up until the final nth term, where we have ar to the power of n minus 1. So what exactly are we doing over here? Well, you can see the first term is a. We're multiplying each time by r. So let's just show this information. You can see here we have the first term, which is a, and then each time we are multiplying by r to find the next term. So to go from a to ar, we times by r. To go from ar to ar squared, we times by r. To go from ar squared to ar cubed, we times by r. So this over here is our common ratio. Let's just write this down. We have common ratio of r. Now, let's suppose over here we want to add all these terms together. If we do that, we have a, our first term, plus our next term, ar, plus the term after this, ar squared, plus ar cubed, and we continue this up until ar to the power of n minus 1. And if we add all of this together, hopefully here you can see all of this is equal to a, lots of r to the power of n minus 1 divided by r minus 1. And you've met this result during the A-level maths course. So what exactly are we doing over here? Well, hopefully you can see here we're summing ar to the power of n from n equals 0 to n equals n minus 1. Okay? And this makes perfect sense, doesn't it? When n is equal to 0, we have ar to the power of 0, which is a. When n equals 1, we have ar to the power of 1, which is ar. When n equals 2, we have ar to the power of 2. When n equals 3, we have ar cubed. And then our final term, when n is equal to n minus 1, we have ar to the power of n minus 1. So this result over here makes complete sense. And similarly, if we have the sum from n equals 0 to n equals infinity of ar to the power of n, well, hopefully here you can see when n equals 0, we have ar to the power of 0, which is just a. When n equals 1, we have ar to the power of 1. When n equals 2, we have AR to the power of 2. When n equals 3, we have AR to the power of 3. And we continue this up until infinity. And if we add all these together, similar to what you've met in A-level maths, it turns out here we get A over 1 minus R, where the mod of R is less than 1. So everything I'm talking about now is just what you've met in A-level maths. So we can extend this idea forward with complex numbers. Let's suppose you've got a complex number W and another complex number Z. So W and Z belong to a set of complex numbers. The sum of W times by Z to the power of R from R equals 0 to R equals n minus 1. That's shown here. When R is equal to 0, we have W. When R equals 1, we have WZ to the 1, which is WZ. When R equals 2, we have WZ to the power of 2. When R equals 3, we would have WZ cubed, etc. And we continue this up until R equals n minus 1, in which case we have WZ to the n minus 1. And if we add all this together, we get W lots of Z to the n minus 1 over Z minus 1, where W is the first term and the common ratio is Z. And similarly, if we have the sum from R equals 0 to R equals infinity of WZ to the power of R, when R equals 0, we have WZ to the 0, which is W. When R equals 1, we have WZ to the 1, which is WZ. When R equals 2, we have WZ to the power of 2. And we continue this up until infinity. And if we add all these terms together, we get W over 1 minus Z, where W is the first term and Z is the common ratio. And the mod of Z, of course, has to be less than 1. So these results match the corresponding results for real numbers. And notice for the infinite series, the sum from R equals 0 to R equals infinity of WZ to the R converges only when the mod of Z is less than 1. So essentially, we will be building up on what we've learned in A-level maths, but applying those results to complex numbers. Example number 13. We're given that Z is equal to cos of pi over n plus I sine of pi over n, where n is a positive integer, and we have to show that 1 plus Z squared plus terms up until Z to the n minus 1 is equal to 1 plus I cot of pi over 2n. Now if you compare with what we have over here with what we have over here, hopefully you can see, if we compare each term, we've got the W here and we've got the 1 here. We've got a WZ here and a Z here. We've got a WZ squared here and a Z squared here. We've got a WZ to the n minus 1, and here we've got a Z to the n minus 1. Straight away you should be able to spot W is equal to 1. So if we consider the left hand side of this equation, hopefully you can recognize we have the sum from R equals 0 to R equals n minus 1 of Z to the power of R. And if we tidy all of this up, comparing with what we have over here, with W equaling 1, we have 1 plus Z squared plus terms up until Z to the n minus 1. And if we use what we have over here with w equaling 1, this is equal to z to the power of n minus 1 over z minus 1. And our goal is to get this bit to look something like this. Now, straight away you can probably spot the argument of z is equal to pi over n. But over here we've got a pi over 2n. So that already makes things a bit more complicated. So what we can do first of all is replace the z with what we have over here. So if we do that, z to the n, we have z which is equal to cos of pi over n plus I sine of pi over n. We raise this to the power of n, we then subtract 1, and then all of this result we will divide by z, which is cos of pi over n plus I sine of pi over n. So that's what z is, and then we subtract the 1. And if we use Demoivre's theorem to help us simplify this even further, you can see on the top, if we bring this power into the argument, we have cos of pi n over n plus I sine of pi n over n minus 1. So all we've just done over here is use Demoivre's theorem. The bottom is not going to change. On the bottom, we still have the cos of pi over n plus I sine of pi over n minus 1. And you can see the n's over here cancel. So on the top we have the cosine of pi plus I times by the sine of pi minus 1. And on the bottom we have cos of pi over n plus I sine of pi over n minus 1. Still, things are looking quite complicated. Now, if we pay attention to what we want to show and what we have over here, I think it will help if we look at the right hand side and think to ourselves how we can get to this right hand side. So far we have 1 plus I cot of pi over 2n. Now, at this point I'll probably think to myself, cot is the same as cos over sine. So cot we're going to rewrite as cos of pi over 2n over the sine of pi over 2n. And don't forget, we still have the I over here. And we can rewrite the 1 so we've got the same denominator. So if we do that, on the bottom we've got the sine of pi over 2n, and on the top we have sine of pi over 2n. This is the same as 1. This is the same as I cot of pi over 2n. We've got the same denominator, so perhaps we can simplify all of this by combining these fractions. We have the sine of pi over 2n plus I cos of pi over 2n, and on the bottom we've got the sine of pi over 2n. So at some point we need to get this line, then we can move on to this line, and then we can complete with this line over here. So on the bottom, we want a sine of something on the bottom only. Now, how could we get that? Before we do anything, let's simplify the top, recognizing that the cosine of pi is equal to -1. We've got -1 minus another 1, which is -2. Sine of pi, that's 0. So on the top, hopefully you can see we've got -2. And on the bottom, we've got cos of pi over n plus I sine of pi over n minus 1. And again, we want the sine of an angle to be on the bottom only. And if you pay attention to what we mentioned over here, on the top we've got a I. So how could we do this? This will require a fair bit of work. So, to make our lives a little easier, I think it might be a good idea to write all of this in exponential form. So on the top we get -2, that's not going to change. But on the bottom, if we write the bottom in exponential form, you can see here we have e to the power of pi I over n minus 1. Now, if you pay attention to what we want to show, and we talked about the various steps as well, you can see here there is a sine of pi over 2n, and here we have an e to the power of pi I n minus 1. Now, we have to think to ourselves, what involves e's and sines? And once we figure that out, we can figure out sort of how to go from here to this step. Because once we're at this step, we can go to this step, to this step, to this step. So you may remember from previous videos this idea over here. Sine of n theta equals 1 over 2i, lots of e to the I n theta minus e to the minus I n theta. So essentially, we might be using this over here. So let's just write it down just for the sake of clarity. We've got the sine. Now obviously over here, if you look back at what we wanted to show, we've got a sine of pi over 2n. So if we replace the n theta with pi over 2n, so we're replacing the n theta with pi over 2n, you'd find here we get 1 over 2i, okay, multiplied by e to the I pi over 2n minus e to the minus I pi over 2n. Now, why is this useful? Because if we multiply through by 2i, you can see here 2i sine of pi over 2n is equal to e to the I pi over 2n minus e to the minus I pi over 2n. So let's see what we can do with this. If you pay attention to what we have on the bottom over here, we've got a e to the pi I n minus 1. And if we compare that with what we have over here, well, essentially, we want to replace this bottom bit with just this bit over here. Okay? So the question is, how can we do that? Well, let's think about this. Well, e to the minus something, that's 1 over e to the something. So 2i multiplied by sine of pi over 2n is equal to e to the I pi over 2n minus 1 over e to the I pi over 2n. And still, we want to make this similar to the bottom over here. And you may recall as well, and it's quite crucial you remember this, we just want the sine of pi over 2n on the bottom. So you'll notice over here we have a minus 1, and here we have an e to the pi I over n. But over here we've got an e to the I pi over 2n. So for us to get a 1 over here, we can multiply both sides by, we'll just write it down in a different colour, we can multiply both sides by e to the I pi over 2n. So if we do that, we have this result times by this, so this turns out to be 2i e to the I pi over 2n times by the sine of pi over 2n, and this is equal to e to the I pi over 2n, lots of e to the I pi over 2n minus 1. And we can tidy this result up over here. So we can tidy this result to give us e to the I pi over n. And then we still have the minus 1. And this is what we have over here. So hopefully what you can now see, we can replace this bit with essentially what we have over here. And if we do that, let's just write this down. So what we've managed to do somehow is find something for the bottom term. On the top, we've got this minus 2, and on the bottom, we have this result over here, 2i e to the I pi over 2n times by the sine of pi over 2n. And what we can now do is somehow, for us to get the sine of pi over 2n over here, we need to divide the top and bottom by e to the I pi over 2n. So if we do that, on the top we've got minus 2 divided by e to the I pi over 2n, okay, and on the bottom, we just write down what we have on the bottom. We have 2i e to the I pi over 2n times by the sine of pi over 2n. And remember, we just want the sine of pi over 2n on the bottom. We'll deal with the top later. And obviously we're going to divide this entire result by e to the I pi over 2n. So this term and this term will cancel out. And rewriting this on the top, we have minus 2 e to the minus I pi over 2n. That's what we have on the top. And on the bottom, we just have, because the e to the I pi over 2n cancels, we just have 2i sine of pi over 2n. Now what is minus 2 over 2i? If we go to our calculator, we're in complex mode already. Minus 2 divided by 2i, you'd find this to be just I. So on the top, you'd find we get I times by e to the minus I pi over 2n, and on the bottom, we have sine of pi over 2n. So we're making some sort of progression over here. What we can do is write this exponential form of a complex number in mod arg form. We still have this I, we'll leave that alone for a second. And e to the minus pi over 2n, you'd find this to be, if we open up a big bracket, the cosine of minus pi over 2n plus I sine of minus pi over 2n. Okay, and on the bottom, what you'd find over here, we still have the sine of pi over 2n. Now how does this help us? Well, hopefully what you can see over here, if you remember, what do we want to show? We want to show somehow we get to this line over here, from here. And you'll notice here we have a positive pi over 2n instead of the minus pi over 2n. So the way we can go about this to simplify all of this, we can replace the minus pi over 2n with positive pi over 2n, and then cos of a negative angle is equal to cos of that positive angle. So here we've got cos of pi over 2n, okay, and of course with here sine of a minus angle is equal to minus sine of the angle, because sine is a odd function. So here we get minus I sine of pi over 2n, okay. And on the bottom, we still have this result over here of sine of pi over 2n. So the question is, how do we simplify all this? Well, a good place to start will be to expand the brackets on the top. And that's actually a good idea if you think about it, because if we pay attention to what we want to show over here, you'd notice if we expand the brackets, we have a I times by the cosine of pi over 2n, which is what we get over here. So we're making a lot of progress now. Expanding these, we have I times by the cosine of pi over 2n, and then we have I times by minus I, so that's minus I squared, times by the sine of pi over 2n. And on the bottom, we have the sine of pi over 2n. Now, what is I squared? That's minus 1. So this result over here is positive sine of pi over 2n because minus I squared is just positive 1. And then over here we have the I cos of pi over 2n. And then on the bottom, we have the sine of pi over 2n. Now, all we have to do over here, now that we're at this stage, which is what we have over here, we need to work backwards to get to here. So, if we do that, we have I cos of pi over 2n divided by the sine of pi over 2n, and then we add on, as we can see over here, sine of pi over 2n over the sine of pi over 2n. This result over here is just 1, so we have plus 1. And this result over here, well, we still have the I, that's not going anywhere. Cos divided by sine, that's just cot. So we have cot of pi over 2n. And you'd find this is the result which we wanted to show. Again, if we go back to the question, you'd find indeed that's what we get. So when it comes to doing questions like these, I think it's a good idea to pay attention to what you want to show. And then from there, that can help you figure out the steps you need to do to figure out these sorts of answers. Consider a geometric series. Okay, so let's suppose we have our first term, e to the I theta. Now, if we have a common ratio e to the I theta, and let's suppose we have n terms, then the next term will be e to the 2I theta. The term after this, we have e to the 3I theta, and we can continue this up until we reach the nth term, where we have e to the ni theta. So we have over here our first term. So this is our first term. And you can also see that the common ratio is e to the I theta. Okay, so this is the common ratio. Now, if we add all these together, the sum of the series, we'll call this Sn. If we use what we mentioned at the start of this video over here, okay, then what you can hopefully see, we've got the first term here, which is essentially what the W is. So if you match everything up, we have here e to the I theta, so that's the W bit, multiplied by z to the n. Now z is our common ratio, so we multiply by e to the I e to the ni theta. Now the reason I'm multiplying by n is because we're raising this to the power of n, and then we have minus 1, and then we divide this by z minus 1, so we divide by e to the I theta minus 1. Okay, so how does this help us? Well, if we write everything in modulus argument form, So if we write all of these in modulus argument form, so let's just write this down. We have here cos theta plus I sine theta, okay, so that's this term here. E to the 2I theta, that's going to be using Demoivre's theorem, cos 2 theta plus I sine 2 theta, okay. For this term over here, we have, again using Demoivre's theorem, cos 3 theta plus I sine 3 theta. And we can continue this up until the nth term, where we have cos n theta plus I sine n theta, okay? And if we gather the real and imaginary parts separately, for the real parts we've got over here cos theta, then we've also got the cos 2 theta, and then we've got the cos 3 theta, and then we've got the other terms up until we reach the nth term where we've got cos n theta. And then for the imaginary terms, we've got sine theta plus sine 2 theta plus sine 3 theta, and then we continue this up until the nth term where we have sine n theta. And we know that all of this is equal to this. So therefore, what we can conclude from here is cos theta plus cos 2 theta plus cos 3 theta, etc. up until cos n theta, because this is real, it will equal the real part of this. So this is equal to the real part of e to the I theta, lots of e to the ni theta minus 1 over e to the I theta minus 1. And if we do the same thing for the imaginary parts, we've got sine theta plus sine 2 theta plus sine 3 theta, and then we continue this up until the nth term where we have sine n theta. This is equal to the imaginary part of what we have over here. We have the imaginary part of e to the I theta, lots of e to the ni theta minus 1 over e to the I theta minus 1. So everything I've mentioned over here is set out clearly in the notes over here. 14. We have s, which is equal to e to the I theta plus e to the 2I theta plus e to the 3I theta, etc. up until the final term e to the 8I theta, for theta not equaling 2n pi, where n is an integer. And we have to show that s is equal to e to the 9I theta over 2 times sine of 4 theta over the sine of theta over 2. So how would we go about doing something like this? Well, of course we'd have to use the knowledge which we've mentioned over here. You can hopefully see we have the sum of this series S. So using this idea over here for part A of the question, we have S, which is equal to e to the I theta plus e to the 2I theta plus e to the 3I theta plus terms up until e to the 8I theta. And we know that this all added together is equal to this. So this is equal to, well, we've got our first term. We have e to the I theta. We then multiply this by e to the ni theta, and you can see n is equal to 8, so we have e to the 8I theta, and then we subtract the 1, and then we divide by e to the I theta, lots of minus 1. Okay? Now, let's think about what we want to show over here. We want to show this result over here. Okay? Now, how could we go about doing something like this? This example, first of all, let's pay attention to what we have over here. We have a sine of theta over 2 on the bottom, and over here we have a e to the I theta minus 1. So because we have a sine and we're dealing with exponentials, it might be a good idea to think to yourselves, we need to use this idea over here. So if we use that particular idea, what we have over here then, if we use that, let's just write it down. We have using, let's just write it down here, using what we met over here, we have in our problem, in what we want to show, a sine of theta over 2. So we're replacing the n theta with theta over 2. So this is equal to 1 over 2i lots of e to the, now over here we need to be a bit careful. We're replacing n theta with theta over 2. So here we have I theta over 2 minus e to the minus I theta over 2. Okay, be a bit careful. And then if we multiply through by 2i, we have 2i sine of theta over 2. This is equal to e to the I theta over 2 minus e to the I theta over 2. So we're just using this result over here. The reason for that, if you look back in what we want to show, on the bottom we have a sine of theta over 2. So if you look at what we have so far, we've got a minus 1 over here. Now what we can do is recognize e to the minus something. That's going to be 1 over e to the something. So here we've got e to the I theta over 2 minus 1 over e to the I theta over 2. And this is equal to 2i sine of theta over 2. So what we want to do is get a 1 over here. So the way we can do that is we can multiply, as we did before, both sides by e to the I theta over 2. So when we do that, we have 2i e to the I theta over 2 sine of theta over 2. This is equal to e to the I theta over 2 multiplied by e to the I theta over 2. And then we subtract off 1 because this term times by this just gives the 1. So we can tidy this up a little further. We have over here 2i e to the I theta over 2 times by the sine of theta over 2. And this result over here is just simply e to the I theta. And then we subtract off the 1. So if you pay attention to what we have over here, we have this result over here. Okay? So we can replace this bit with this bit over here. So let's attempt to do that. Okay? So if we replace as necessary, on the top we have the e to the I theta, lots of e to the 8i theta minus 1. We'll leave that alone for a second. But on the bottom, we've got 2i e to the I theta over 2 times by the sine of theta over 2. So how does this help us? Well, e to the I theta over e to the I theta over 2. That will just be, if we subtract the arguments, e to the I theta over 2, and we're multiplying this by e to the 8i theta minus 1. And on the bottom, because we've dealt with this and this, we're just left with the 2i sine of theta over 2. Okay? Now, at this point, we need to tidy all of this up. Okay? Now, if you look at what we want to show, well, we've sort of dealt with the bit at the bottom. We have, as you can see here, a sine of theta over 2. We'll just ignore this 2i for now. But if you look over here, we have sine of 4 theta. But over here we've got a e to the 8i theta minus 1. So we can use the same idea over here to help us get rid of this bit over here, so that we're left with a sine 4 theta. As we said, on the top we want a sine 4 theta, so we're going to have 1 over 2i lots of e to the 4i theta minus e to the minus 4i theta. Okay? So with this, like we did over here, let's first of all multiply through by the 2i. So we've got 2i sine 4 theta equals e to the 4i theta minus e to the minus 4i theta. E to the minus something, that's just 1 over e to the something. So here we have 1 over e to the 4i theta, and here we have the e to the 4i theta, and this is equal to the 2i sine 4 theta. Okay? And as we did over here, let's just multiply through, in this case, by e to the 4i theta. So when we do that, of course, over here, we'll end up with a similar result to what we have on this fourth line over here. We'd have 2i multiplied by e to the 4i theta times by the sine of 4 theta. This is equal to e to the 4i theta times e to the 4i theta minus 1. So over here we have 2i e to the 4i theta times by the sine of 4 theta. Here we get e to the 8i theta minus 1. So what we will now do is replace this bit with what we have over here. Okay? So if we do that, we have e to the I theta over 2, we'll leave that alone for a second. But this bracket over here, hopefully you can see that's just, as we said over here, 2i e to the 4i theta sine 4 theta, and on the bottom we have 2i sine of theta over 2. So how does this help us? Well, what you can hopefully see, the two i's cancel out. So we have e to the I theta over 2 times by e to the 4i theta times by 4 theta. That's what we have on the top, and on the bottom we're left with sine of theta over 2. Now e to the I theta over 2 times by e to the 4i theta, that's just e to the 9i theta over 2, and then we multiply this by sine of 4 theta, and then we divide by sine of theta over 2. So this is the result which we wanted to show over here. Now for part B of the question, we have to let p equal cos theta plus cos 2 theta plus cos 3 theta, etc. up to cos of 8 theta, and we have to let q equal sine theta plus sine 2 theta plus sine 3 theta, etc. up until sine 8 theta. And now we have to use our results in part A to show that p equals cos of 9 theta over 2 times by the sine of 4 theta times by the cosec of theta over 2, and we have to find similar expressions for q and q over p. So to do this, what we need to do over here is recognize what we mentioned before. What we said over here is cos theta plus cos 2 theta plus cos 3 theta plus terms up until cos n theta is equal to the real part of s, where s is this result here, and sine theta plus sine 2 theta plus sine 3 theta up until sine n theta, that's equal to the imaginary part of s, where s is this result over here. Now, what we found in part A was s is equal to this result over here. So let's just write that down. We know that s is equal to e to the 9i theta over 2 times by the sine of 4 theta divided by the sine of theta over 2. So when we come to look at what p is, p obviously is the real part of s. So let's just write this down. P, which is equal to cos theta plus cos 2 theta plus cos 3 theta up until cos 8 theta. Okay, this is equal to the real part of this result here, which is s. So we're looking at the real part of e to the 9i theta over 2 times sine 4 theta over sine of theta over 2. Okay, now before we work anything out, what we can do to help us simplify all of this e to the 9i theta over 2 using Demois's theorem, that's equal to cos of 9 theta over 2 plus I sine of 9 theta over 2, and this is being multiplied by sine 4 theta. Now of course, sine of theta over 2, you'd find to be cosec of theta over 2. Now, the reason I use the cosec is because in the show that we have to use the cosec. So, what we're looking for in this question, P is equal to the real part of this result over here. So we're looking at the real part of cos 9 theta over 2 plus I sine of 9 theta over 2 times by sine 4 theta times by cosec of theta over 2. Okay? So the real part, well, we're not going to include I times by this term, so the real part will simply equal cos of 9 theta over 2 times by sine 4 theta times by cosec of theta over 2. And now for the expression for Q, we simply use the same idea. So we know that Q is equal to sine theta plus sine 2 theta plus sine 3 theta plus terms up until sine 8 theta, and of course this is equal to the imaginary part of this result, so it's equal to the imaginary part of 9I theta over 2 times by sine 4 theta over sine of theta over 2. So if we use what we have over here, we're looking at the imaginary part of cos of 9 theta over 2 plus I sine of 9 theta over 2 times by the sine of 4 theta times by the cosec of theta over 2. Okay, so we want the imaginary part of this. Well, we're not going to include the cos of 9 theta over 2 times by this. That will give a real part. So the imaginary part, that will simply equal sine of 9 theta over 2 times by the sine of 4 theta times by the cosec of theta over 2. So that's what Q is. And now we have to find Q over P. So therefore, just put therefore symbols over here. Q, and we're going to divide this by P. Q divided by P, that's equal to, well, we've got Q, which we've just found to be sine of 9 theta over 2 sine of 4 theta times by the cosec of theta over 2. And then we divide this by what P is, which is cos of 9 theta over 2 sine of 4 theta times by cosec of theta over 2. So what we end up with over here then, if we tidy this up, you'll notice this all cancels out. We're left with the sine of 9 theta over 2 over the cosine of 9 theta over 2, which is simply tan of 9 theta over 2. So therefore Q over P is equal to tan of 9 theta over 2.